All right, what we're going to do now is hone in on a very special type of oscillatory motion that's known as simple harmonic motion. And what I want to do is just kind of, at this point, introduce what simple harmonic motion is, and then look at the graphs for simple harmonic motion. This isn't an overly mathy part. We're going to reason using some math, but we're not going to be doing equations yet. But simple harmonic motion is really the most basic type of oscillatory motion you can have. In fact, the cool thing is you might learn in some of your later engineering courses that more complicated forms of oscillation can actually be viewed as a product of simple harmonic motion, just a bunch of different simple harmonic motions being added together to create the overall effect. So this is really fundamentally important. You've got to understand this type of oscillatory motion to be able to move on later and understand more complex forms of oscillatory motion. So right now we're just going to focus on understanding what simple harmonic motion is, where it arises from, and then looking at the graphs of it. So in essence, simple harmonic motion is just a form of oscillatory motion where the position varies sinusoidally with time. Sinusoidally means that the motion can be described using either a sine function or a cosine function. I will go ahead and tell you we're going to be using a cosine function to describe simple harmonic motion, or SHM. But it's just that the object's moving and the position as a function of time is varying sinusoidally. We would see this in an experiment we could actually set up in our lab. Say we had a mass that was on an air track. You've messed with those before in lab. Let this mass be attached to a spring, okay? The spring has been pulled back and the object is oscillating back and forth between the two amplitudes, okay? Well, at this point, we're going to assume that the object is moving towards the maximum negative amplitude. It's not at its equilibrium position because equilibrium would be here in the middle. Now, if we were to graph out the position, the distance from the equilibrium as a function of time, and we were just to take snapshots, say we had a sonic ranger down here that was measuring position every so often, then if we were to graph out those specific positions as they flowed out over time, we would get a graph that looks something like this. Now, this graph's going to be turned sideways, so be prepared for that. But here it is. So here we have our x-axis drawn out this way to correspond to the track, so we can kind of line up our x with the orientation of the track. And then the time axis is running down here through the middle. And of course, here's our maximum positive amplitude, here's our maximum negative amplitude, and equilibrium is going to be right here, it's smack in the middle of the two of them. Well, for an object attached to a spring, if we were to, put down points to represent its position at discrete units of time, this is what the graph would look like. You can see that as time goes on, the distance the object's traveling each time is getting a little bit smaller until it's out here at the maximum amplitude, and then the distance each, say, second or millisecond or whatever, is getting larger as you go back towards the equilibrium. And we could map this out throughout so more than one cycle, and this is what it's going to look like. Well, that should be a somewhat familiar shape to you from your calculus and your trig courses. This is the graph of it could be either a sine or cosine function, but it's sinusoidal in nature. And that's the way an object that's attached to a spring moves. We could actually derive that using Newton's laws. We could get the position as a function of time, the equation for that using Newton's laws and applying it to Hooke's law acting on this mass from this spring. But, we could also actually just go into the lab and get the result. And so this mass, as it oscillates back and forth, it's not moving at a constant velocity each second, because as it gets out here close to the edge, it's got to start slowing down so it can turn around and go back the other direction. And what that results in is a sinusoidal shape to the motion graph, okay? Now, we could describe that using a cosine or a sine function. I will say what we're going to use is a cosine function. It works. We could use a sine, but cosine is generally the way in physics that we describe simple harmonic motion. But that's really just a choice because a sine and a cosine have the same shape. They're just separated by a certain phase or a certain amount of radians or degrees, right? But you could pull a cosine function back and it would lay straight over a sine function. So that's a choice. We make a convention, and so we use cosine. That's what we're going to use. Perhaps you can see the shape and the sinusoidal nature a little bit better if I turn everything over on its side. So I've flipped this around, and just so you can see this, if we were to, I think it's a little bit more obvious this way. Yeah, I've got some sort of cosine or sine function that's working here. But what I want you to know is that's simple harmonic motion. It's something that's oscillating, and its position function is described by a sine or a cosine function. That is simple harmonic motion. All other forms of oscillatory motion can actually be built up as a sum of a bunch of sines and cosines with appropriate amplitudes in front of them. We'll talk more about that in a little bit, but this is the nature of simple harmonic motion. Now, I want us to look at the graphs just real quickly for what this would look like. I went into Desmos's graphing calculator online, and I know what the equation is for it, so I've plugged that in, and I've created a graph for an object that's undergoing simple harmonic motion. Now remember, we can look at the graph and read some important things off, right? The amplitude is obviously 2 centimeters, right? So its maximum positive amplitude is 2 centimeters. Its maximum negative amplitude is negative 2 centimeters, okay? We can also read the period of this off. It goes, we just need to find 2 points that are in the same place of motion. So I tend, if I can, on my graph, to go from the maximum positive amplitude to the next maximum positive amplitude. And you can see the time between this point and this point, it goes from 0 to 8 seconds. So the period is 8 seconds. And we could get the frequency if we wanted to. That would just be 1/8 hertz because it's the inverse of the period. So there's a graph of simple harmonic motion. And just like that kind of made-up example in that first video, we can start getting important information about the motion right off of the graph. But I want to look at velocity considerations because you know now that the position is going to vary sinusoidally. But if that's the case, what are the implications then for the velocity of the mass that's attached to the spring? Okay, well, let's think about that. Let's use the simple fact that velocity at any given time is the slope of the position function. All right. Now you've learned in calculus that if you have a graph, or a graph that's not a straight line, then the way you calculate the velocity at any specific point is you have to take the derivative. And of course, that derivative is just the slope of the tangent line at the point where you want to know the velocity. And that's what you're finding when you take a derivative. Well, let's just conceptually think about it. Let's go up here to the maximum positive amplitude that occurs at t equals 0, right up here. Okay? If I were to draw in the tangent line, that tangent line is going to be horizontal. Now, what's the slope of a horizontal line? It's 0, right? Okay, so what this tells us is that at the maximum positive amplitude, the velocity of the mass that's attached to that spring has to be 0. And that makes sense, doesn't it? Because think about what's going on. As it moves out to its maximum positive amplitude, it's got to stop and turn around so it can start going back the other direction. So we would expect that at the maximum positive amplitude, the velocity should be 0, and our graph shows us that. Now, let's go down here to where it crosses the equilibrium point. Well, hopefully you can see, if I were to draw in the tangent line, oh, I'm sorry, we'll come back to that. I wanted to show you what happens at the maximum negative amplitude. Well, again, we get a horizontal line, and a horizontal line slope is 0. So when it gets out here to the maximum negative, then the velocity is once again 0. And that makes sense too, I hope, because as the object gets to that maximum negative amplitude, it's got to turn around and start going back the other way. So if it turns around, it's got to stop for an instant of time, and its velocity is going to be 0. And you can see that this is going to be the case every time it reaches its positive or its negative amplitudes. They're always going to be 0. So anytime that object is at its extremes, for that instant of time that it's there, its velocity is 0. It's sitting still for an instant of time. But now let's look at what happens then when we get to the equilibrium positions. Well, let's consider this one first. If I draw in the tangent line, That's what it's going to look like. Now, the first thing I want you to think about is between here and here, this is the point at which the tangent line is going to be the steepest. You can see that. It goes from 0 all the way down to this point. So it's increasing in its slope till it gets here, and then it starts to decrease and decrease because it's got to get back to 0. So at the center is where the tangent line is going to have the maximum slope. So this is the point where your velocity is going to have its maximum value. Now in this case, this is where it has its maximum negative value because the tangent line has a negative slope. And so as it's moving from the positive amplitude down to the negative amplitude, when it crosses the equilibrium position, that's the fastest it'll be moving, going from positive to negative. So it has its maximum negative value at in this case, 2 seconds, okay? But it's right in the middle at equilibrium between the amplitudes, okay? You're always going to have your maximum. If you want to talk about it in speed, the speed is the greatest at equilibrium. But we want to talk about velocities too, because velocity is a vector and we need to know direction. Well, what happens when we get over here to this 6 seconds? Because we're back at equilibrium again. Well, if I were to draw that in, my tangent line, again, this is where it's going to be the steepest. Any tangent line between here and here is not going to be as steep as this one. Same case for going from here to here. So this is again where we're going to have a maximum value, but this time it's positive. And so at 6 seconds, as it's moving from its maximum negative amplitude up to its maximum positive amplitude, when it crosses equilibrium, it's going to have its net velocity is going to have its max positive value. And again, this scenario is going to flip-flop as we go throughout further cycles. When we get to 10 seconds, we're going to be back to the max negative value for velocity again. When we get to 14 seconds, we're going to be back at the max positive value again. And so what we see then is that this velocity kind of varies in a very repetitive, predictable fashion. In fact, we've noticed that the velocity is going to be 0, okay, when it's at its amplitude, so that oscillator sits still for an instant of time, and then it's going to have its maximum positive and negative values when it passes through equilibrium. And whether it's positive or negative depends on which direction it's moving at that point. Negative, it's moving from the positive side to the negative side. It's going in the negative direction. Positive, it's going from the negative side to the positive side. It's moving in the positive direction. Now, we've kind of reasoned conceptually about how the velocity is going to vary throughout the oscillations, but let's actually draw the graph. If I were to graph this, then the graph is going to look something like this. If you notice, first of all, it all works according to what we've reasoned out up here. We said at the maximum positive, or at any of our amplitudes, the velocity's got to be 0. So we come down from this amplitude, velocity 0. We come down from this amplitude, the velocity is 0. And again, this is velocity on this axis, time on this axis. If we come to this amplitude, go down, the velocity is 0, and so on. So this graph does meet our requirements based on our knowledge of calculus and velocities and how that can be derived from the function of position. Okay, our maximum our maximum negative and positives have to occur at equilibrium. And so if you look, first of all, the velocity is going to be negative all the way through here, and it's negative in that whole range. These are all negative velocities. But the maximum's got to occur at equilibrium, and sure enough, that's what we get. We get a maximum down here. And then coming back up, all these velocities have to be positive, and sure enough, that's what we get. All the velocities are positive, and again, the maximum's going to have to occur at equilibrium, and look what we do. We get a maximum. The cool thing is, the velocity, the maximum positive velocity and the maximum negative velocity are going to have the same magnitude, just like this guy up here has the same amplitudes. In fact, you could think of a velocity function that has an amplitude that's equal to the maximum positive and negative velocities of the oscillator. Okay? So, you know, that's just kind of how this varies. The other thing I would point out is if you think about it, go back to your calculus. What do you get? This is a positive cosine function. When you take the derivative of a cosine, what do you get? You get a negative sign. So you'd have a sine function but flipped upside down. And that's exactly what we have here. This graph is just the derivative of this graph. And so we know that velocity is the time derivative of position. And so that's the basics of graphing. And so I'm just wanting to introduce very conceptually here what goes on with simple harmonic motion. We're going to get into a little bit more math in the next video, but I hope you're taking notes. Again, I'm going to remind you of that all the time. And if you have any questions about this, contact me.